Hello students, welcome back to another video. Today we're going to be discussing the magnetic force. We'll learn about how the magnetic force works and why it works. Magnetism is very closely related to electricity. The way the magnetic force is related to electricity is because the magnetic force is generated whenever charges move. Okay, so yesterday we learned that there's an electric force between different charges, either an attraction or repulsion depending on the two charges. Like charges repel and opposite charges attract. Whenever these charges are moving, or whenever they have a velocity, they make something called a magnetic field, which applies a magnetic force on other charges. Okay, so anytime you have electrons flowing and moving around, a magnetic field is made that applies this magnetic force. I'm going to draw a picture of a magnet and demonstrate what's happening. In the case of a permanent magnet, the electrons in this magnet spin in a way to create a magnetic field which flows from the north pole of the magnet to the south pole of the magnet. Okay, so here I've drawn those magnetic field lines where they come out of the north pole and then they move towards the south pole in this loop fashion. So this magnetic field that is looping around this magnet will cause a force on other things that have charges that come by it. So if I bring another magnet close to this magnet, it will feel a force that either repulses or attracts it. If I bring the north pole of the other magnet close to this north pole, it will repel it. But if I bring the south pole close to this north pole, it'll immediately attract that other magnet and it'll link together. So here I've drawn a picture where I bring in another magnet. The north pole of the second magnet is going to get attracted to the south pole of the first magnet, and then they'll ultimately just create a bigger magnet where the electric field lines will go from the north pole here all the way to the new south pole. These types of magnets are called permanent magnets, but the magnetic force can also exist in other cases whenever charges are flowing. For example, whenever currents run through wires, there is a small magnetic field that loops around that wire of moving charges. Okay, now I'm going to show you something called the right-hand rule. We can use this right-hand rule to relate the direction of the magnetic field to the direction of the velocity of the charge and to the direction of the force from this magnetic field. Before I get into the right-hand rule, I want to talk about the notation that we use. For force, we use an F. For the velocity of the charge, we use a V. And for the magnetic field, we use a capital B. Okay, so whenever a charge is moving, it has some velocity. As a result of that charge moving, a magnetic field is generated. And when other charges are in the presence of a magnetic field, they feel a force. Now I'm going to talk about the right-hand rule, and I'm going to draw some examples that can help you understand it. Okay, let's say I have two magnets at some distance apart, and I have the north pole of this magnet facing the inside and the south pole of this magnet facing the inside. So between these two magnets, there is a magnetic field created. Just like I showed you with the permanent magnet, magnetic field will be pointed from the north to the south pole. So here I've drawn my magnetic field lines in green ink, and I've labeled that with a capital B to notate that's the magnetic field flowing from north to south. Let's say I drag a positive charge into the center of this magnetic field, and I want to know what force is applied to this charge as a result of being in this magnetic field. And let's say I shot this positive charge into the magnetic field in a way that it had a velocity going upward. So I've drawn a vector going up from the charge, and I've labeled it a V for velocity. The right-hand rule will tell me where the force vector will point for this charge in this magnetic field. Down here, I've written out the right-hand rule. It's kind of cramped down here, but I'll explain everything. So because this is called the right-hand rule, we're going to use our right hand, not our left hands. We're going to point our thumb in the direction of the velocity, our fingers in the direction of the magnetic field. You have to make sure that your hands is straight. And then wherever your palm points for a positive charge, and in the case of a negative charge, use the back of your hands, is going to be the direction the force points. That might be a lot to take in right now, but as I go through some examples, it'll start to make more sense. In the case of this example that I've already drawn, I'm going to point my right thumb in the direction of the velocity, so upward, and my magnetic field is going from left to right, so I need to point my fingers in that direction. So now I have something like this going on where my thumb points up, my fingers point to the right, and because this is a positive charge, I'm going to use my palm to find the direction of the force. So my thumb is pointing up, my fingers are pointing right, and my palm is pointing into the board, which tells me that my force is into the board. Okay, to notate that the force is going into the board, I draw a circle with an X. This tells me that the force is going this way for this charge as a result of being in this magnetic field and moving in that direction. Let's run through the hypothetical situation where instead of the charge moving up, it was moving down. And let's see how that changes things. Okay, my magnetic field is still going from left to right. I still have a positive charge, but now my velocity is pointing down. So I'm going to point my thumb downward with my right hand, and I need to make my fingers point from left to right. So this is a really awkward hand position for me, but if I point my thumb downward and my fingers to the right, my palm is going to be facing outward now. Okay, so now that the velocity is going downward, the force is coming out of the board. We use a circle with a dot to notate that something is coming out of the board. Okay, I'm going to go through a couple other examples, and this time I'll use a negative charge, and I'll change the direction of the magnetic field. Okay, now I've changed the magnets so that the North Pole is here and the South Pole is there, which means the magnetic field points from right to left. Now I have a negative charge, and I know that's moving downward. Okay, so going with the right hand's rule, I'll point my thumb in the direction of the velocity, so downward. My fingers in the direction of the magnetic field, so this way. And then because it's a negative charge, I use my backhand instead of my palm to find where the force is. In this case, the backhand is facing away from the board, so my force is going out of the board. Okay, so there's my force. So using the right hand's rule, we can find the direction of velocity, magnetic fields, or force. As long as we have 2 out of the 3 pieces, we'll be able to find the third piece. In these examples I just showed you, I started off knowing the magnetic field and the velocity to find the force, but I could also tell you the force in the magnetic fields and let you find velocity, or I could give you the velocity and the force and let you find magnetic fields. If you can figure out where 2 of these things point, you'll be able to find the third one. Okay, I'm going to go through one more example where I tell you the force and the velocity of some charge, and we have to find out where the magnetic field is pointing. Okay, so here I've drawn a picture of a positive charge that's moving to the right, but it feels some magnetic force going downward. So we're going to use the right hand rule to figure out where is this magnetic field pointing. So I'll start with my thumb for the velocity. It points to the right, and I don't know my magnetic field yet, so I'm going to skip to figure out where the force is pointing. And in this case, since it's a positive charge, I'm going to use my palm, and it's directed downward. So I have my thumb pointing to the right, my palm pointing downwards, and where my fingers are pointing is where the magnetic field is pointing. In this case, it's going out of the board. Okay, so with the right hand rule, I was able to figure out that the magnetic field is coming out of the board. So a positive charge moving right through this magnetic field will feel a downward force. Now we'll do one last example where I give you magnetic field and force, and you have to find velocity. Here I've drawn a picture of a negative charge in a magnetic field that is pointed upward, and it is feeling a force into the board. And I want to know where's the direction of the velocity, where is it moving at this exact moment. So I'll use my right hand rule to piece together the information I have. I don't have my velocity yet, so that's what I'm trying to figure out, so I'll skip that. I'm going to point my fingers in the direction of the magnetic field, so upward. And since this is a negative charge, I'm going to point my backhand towards the force, which is going into the board. So the back of my hand points towards the board, my fingers point upward, and my thumb is the missing piece. It tells me the direction of the velocity is going to the right. Alright, there we go. So I was able to figure out where the velocity points for this electron. Okay, so the important takeaways from today's video is to understand that a magnetic force can be generated whenever charges are moving. They generate a magnetic field, which can apply a force on other charges. The other big takeaway from this video is to understand how to use the right hand rule to relate the directions of velocity, magnetic fields, and force for a moving charge that is inside of a magnetic field. So if you're taking notes, I would write this down and keep that handy. That's all for today's video, guys. Thank you. I'll see you next time.